Hi, everyone. Hopefully we've saved something exciting for you. I'll be presenting alongside Michael Luck, who is my awesome boss. Um, so I'll quickly introduce myself. We will be talking about generative AI, kind of playing on some of the RAG talk that you saw from James, and then we'll be highly focused on some industry applications, and then introducing you to some agentic workflows. So just a quick introduction of who we are. My name is Alexis. I work for SFL, which is a Deloitte business, actually co-founded by Mike. I'll let him speak to that a bit. I don't have a physics degree. I actually have a pure theoretical math degree from Rice. I graduated in 2019. I do want to shed a little light on the fact that back then, I knew zero Python. Don't tell Mike that. Completely self-taught since then. During my postdoc, I got introduced to some machine learning projects and just thought it was super cool. I'm a major linear algebra nerd, was through undergrad, like I thought it was the coolest class, and I was always looking for things that used linear algebra. And since then, dive deeply into machine learning and now find myself worked for a startup that did some NLP and document classification. And then now found myself at SFL, where I have again specialized in some NLP type work, but mainly in generative AI development.
Thanks, Lex. I'll give a quick 30-second of myself as well. So previously a Brown PhD person, I worked a lot with Rick on the call. So my background is in physics and sort of transitioned into the world of big data back then, around 10, 12 years ago. And I also started learning like Python pretty late on. I learned AI, on YouTube courses and Coursera and those kind of things. And back then there was no like, data science degrees. Since we started the company, we basically sort of like built sort of an organization around developing AI solutions for customers. So we were always like a consulting company because, well, mainly because it was easier to do and we didn't have to like put money into it. But over time, we grew the company to around 60 folks who 60 folks at our peak when we were acquired by Deloitte about 2.5 years ago. So we got that whole like sort of like life's journey. I like never really imagined myself as an entrepreneur, but we sort of ended up in that work stream of like, delivering good data analytics, data modeling, and rode the AI wave as we went. In the last 2.5 years, I'm now managing director at Deloitte. Oversee the delivery team still at SFL. I also lead what's called the AI Academy, which is like one of Deloitte's initiatives to upskill Deloitte talent in AI. I give a lot of talks similar to the ones I'm hopefully share with you with Alexis today. Really just covering sort of, how do we get people fluent and then how do we get people skilled in, a lot of these nascent technologies. Happy to answer questions on the side and happy to, um, you know, chat offline as well. But that's basically just a summary of myself and happy to be here.
Same. If you have questions just about a journey into AI coming from grad school, coming from academia, whatever it may be, feel free to ping me, ask me anything you'd like. I'm happy to be transparent with you. Um, so to get on to what we'll be talking about today, we're going to give you a little bit of an insight as to what it actually looks like to put specifically generative AI into production. When you actually build tools for clients that they're going to be using or relying on, and then give some examples of what those might look like. Some of the projects we may have done, projects we know of, things like that, things we find interesting. Following up on that, that's where we'll kind of get deep into some of the content. We're going to talk about large language models as a whole. Nothing too technical there, but kind of give you some resources and some places to look if you are interested in going further. Again, just like James did, we're going to talk a little bit about RAG, but I'm again not going to get super technical, just enough for you to build on and to build your tool yourself. We'll dive into some RAG notebook content then. And then we're going to look into something called the React framework, which is a way of using large language models and getting them to use external tools and agents. And then again, go into notebook content, and we're going to develop your own physics research assistant that will, on its own, go and find articles from arXiv and bring them back and give you information that you ask about, all in one workflow, which I think is pretty cool. All right, so on that, I will go ahead and pass it over to Mike.
Cool. So I think for this section, I have maybe 6 or 7 slides that covers sort of like from an organization, from a business perspective, how do we think about AI and Gen AI and developing solutions for them? Really just kind of dry in terms of slides, but I'll give you some examples and layer in, just hopefully give you some sense of like how, these things operate, in businesses these days. So how we see it is really these 5 pillars that we have here across like business strategy and how we build AI strategy. So you can think of these things as like, is your organization that you're working for, are they more focused on net new growth, net new avenues of like aspirational AI and Gen AI, or are they more like efficiency plays or like trying to make people more effective at what they do, right? And so even those kind of conversations around what exactly your business is trying to drive and like how do you align some of your AI strategy around your business goals, right? And this happens everywhere in organizations. And as this Gen AI wave has hit, a lot of the sort of like talk around like, okay, we're focused on XYZ things. We're making sure that the types of AI work that we're sort of investing in matches those aspirations, right? And so I can give you a couple examples. So it's interesting in like say like retail consumer products space where actually a lot of this Gen AI and marketing and sales is like one of those fundamental shifts in how they operate because most of their revenue and performance is measured from the sales that they do for products or what have you. And so for them, it's like one of those things that they're riding and investing a huge amount of money in, right? Whereas for like, traditional, say, distributors, wholesale distributors, who basically ship things in and out, like all of their money is made from making their routing more efficient or making their ability to like fulfill things more efficient, right? And so that's more like a bottom line, trying to drive the efficiencies there. And so each organization has a little bit of nuance of like where they even like play and where they, build use cases. That's the first pillar. The second pillar is around technology, around um, what tech stack you use. And organizations these days generally, span cloud service providers across AWS, Azure, GCP. Like most of them use like a portfolio of different avenues, but also double down on one area because you get, economies of scale, you get, better deals from people selling them and those kind of things, right? And so like as folks figure out which vendors even to use and where do you build solutions yourself or buy them from API calls through different vendors and platforms and hyperscalers we call them, that's one of the big things that you have to like think about in terms of your AI strategy that you develop because some of the tools that you'll see like simple RAG systems that you saw from James, like those will be commoditized in a lot of areas, right? And so those would be very easy to reuse, and companies aren't really looking to build their own RAG system unless it's very tailored to a use case or more specific around things that they're specifically trying to do. I'll skip the middle two because I'm gonna have like a little bit deeper dive in terms of the middle two, but one of them is delivering AI and Gen AI solutions and how we do that in organizations. The second one is talent and culture. One of my favorite topic areas because founding your own company, we use a lot of PhD or ex-PhD folks transitioning industry, and like I have a big just appreciation for how we grow talents. And the last bit is the governance aspect. And for organizations, like you can imagine, any major corporation has to have very controlled like risk management about these new technologies. And there's a huge new risk landscape that exists around, what's possible to, leak confidential information or like for it to hallucinate and you actually take a wrong turn somewhere. And so there's a lot of like new areas where, historically it was just like, good data management. And now it's like that has to extend now to these sort of like nascent technologies that you see. So again, a lot of work that goes on in governance, a lot of paperwork. Not my personal favorite area to focus on, but again, super important just to like make sure that the things that happen and you see in the news um, don't happen to your organization. Because again, even if the big players are doing it, and you saw like news articles about Microsoft and have issues there, that will happen to many people if you're not very careful. And even then, it'll likely have like new things pop up. I think there's an issue with the screen share. Is that true for everybody? I don't know if people can see most of the screen.
Yeah, clearly, very
Okay,
good.
cool. Yeah, so hopefully that's isolated incident. So just moving into the delivery pillar and how we think of things. So I'll cover each of these sort of like steps sort of sequentially. So there's an advised step of like exploring the data that you have available, exploring the solutions, exploring the potential use cases, moving into the implement phase where you're building POCs, MVPs, pilots, in sequence and scaling it out, and then moving into the operate phase where you start deploying this like to thousands, tens of thousands of users and making sure that there's no model drift or data drift and those kind of things. So like we have this framework of A, I, and O, where you naturally flow from more of an exploratory phase to an implement phase to an operate phase. These kind of like aspects, if anyone knows like design thinking, again, it's sort of like that expansion of aperture of what possibilities there are, condensing it down and then going back out to the implement phase, where again, you expand in the POC space of like, find a solution and then condense again. But I won't mention too much about that. Okay, so moving into the advise step, just double clicking a little bit. Oh, next slide. Okay, so the advise step is really around how do we identify use cases? How do we get business value? And this is the standard 2x2 that everyone has in the world of consulting, where you're basically just trying to rank, order, and prioritize where you will find value and how feasible it is to actually do it, right? And one of the examples here I'll give you is last year, maybe the year before now, we worked for a large fast food company. They sell burgers and fries and those kind of things. And they had many different hypotheses around why certain districts in certain areas were outperforming others, right? And so that was their hypothesis, right? And all we had in terms of data sets was ServiceNow tickets. So these were tickets, like ticket issues that classify issues that are happening in restaurants. So you can think of things like, the counter is down, or a power is down, or Wi-Fi is down, or what my favorite one was the meat printer was down. Is what they actually call the thing that makes patties, right? And so if that's down, like it's all hell breaks loose, right? And so there's a lot of different ideas floating around of like why those particular countries had better response times and resolution times to these issues, right? Um, things you can imagine things like there were issues with opening or closing, they were understaffed, there were power outages, or like they had like a big anomaly in Ukraine because of like global geopolitical stuff, and so there's a lot of like hypotheses around it, and we actually narrowed it down to in the U.S. where they were underperforming actually. Um, they would classify incidents in terms of like priority levels, P0 to P5 or what have you, where P0 is like, the whole restaurant is down and we can't sell a burger. And P5 is like, it's like a minor issue, like it'll slow down things by 2% or whatever, right? And in the US, what they did was they classified everything as P0 or P1. So everything was either like super important or just important, right? And so the issue there is like if everything is super important, like no one knows where to prioritize, um, it causes like significant like lag in actually resolving things that cause loss to revenue. Whereas in Germany, they had a nice like Gaussian distribution where you can see like, oh, the things that cause like actual revenue loss are correlated strongly and causally to the issues that they're tagged, right? And these were like, the checkout is down, right? Or the printer is down, the meat printer is down, right? Actual things that were correlated and tagged by humans as an actual issue that caused like revenue loss. And so we basically like, yeah, through this noise and it was like 100 million different tickets and with text free form in there with tags being flown over in different geos in different languages even, found like one or two use cases like this prioritization that were like, here's the thing that's obviously super valuable. If we can get this right, we can drive significant value, right? We can just prioritize things better. There's a good correlation between prioritizing and reducing downtime. That's it, right? And so like quantifying and identifying that was really that advised stage where we're exploring the data set for these signals. And then on top of that, in this sort of like advised stage, you start to feel out what kind of approaches can you do to solve this problem, right? And so what we did was we basically took 2 or 3 days and we trained a model on German ticket data. So we took the text from tickets and predict the priorities. And so we basically just reclassified the US tickets into a German system, right? And so instead of like the P0 it was, it's now P3 because actually the words inside it don't make sense. So we basically just spun up like a simple XGBoost model. We vectorized the text, we shoved it through XGBoost, we predicted it, and we just proved it out on a subset of data where, we can just like showcase that we can actually get signal from the noise. We're like 80% accurate or whatever on a holdout set, and be able to, actually start to build some POC and build some strategy around, how much money, how much accuracy can we do, and is it enough to, justify what in industry would be like $1 million to actually fix, right, functionally. So that's really the advice step of like trying to get signal out of the massive amounts of data that companies are picking up. Okay, that's the advice step. So moving into the implement step, and people have like all these terms for proof of concept, proof of value, pilots, MVPs, all these things. Effectively, we build something that's small in a localized region, small data set, hopefully clean data set. And then you build it, you slightly expand that scope after you can prove it out, and then you expand that scope and prove it out. Alexis and I are actually working on one of these examples where we're working for a wholesale distributor, and wholesale distributors basically have to ship and manage like supplying items to people. In this case, it's like electrical goods, so they have like screws or wires or cables or like apps for junctions and these kind of things. Alexis can talk ad nauseum about electrical cables nowadays. But really, like their issue that we found was that they had, I think, 3,000 or 4,000 different sales associates, and their entire jobs were to take a customer order, and a customer order would be like, oh, I need this 6-foot kind of wire that fits these two outlets, and find in their catalog of 500,000, 1 million SKUs, so 1 million product types, what exact cable has the right resistance, impedance, the right like current load that it can handle, those kind of things, and the right SKU to like recommend back and to actually order and ship to the customer, right? And so to do this, we created actually a RAG, and I think now in a React solution that we'll talk about, where we take the user query and we basically just have like a retrieval augmented system where you pull in, things based on the spec sheets. So you have like, 500,000 spec sheets around like each individual SKU. You pull in the right and retrieve the right, hopefully the right spec sheet, and then you can like just like link back the SKU, right? And so this is an unwieldy problem in that, some cables and some screws are only sold like once every 3 years, right? And so like there's a huge long tail distribution. So in our POC, what we did was we narrowed it down to 1 or 2 different regions and 1 or 2 different product lines. So instead of having 1 million different SKUs, you would have, 10,000, 20,000. Again, a more manageable number, right? And then as we built that out, we're like in phase 2 and phase 3, where we're sort of like fleshing out the number of SKUs and the approach there, right? And as we sort of build it, I think one of the big things that we've discovered that's slightly different in the Gen AI world is that a lot of these systems need like heavy human in the loop, sort of like feedback, right? And so in traditional AI systems, you'd be like, oh, defect, not defect, or like cancer, no cancer. And you can do like 1 million of those in a row. But like bringing the human along, I think is one of the big learnings in this journey around like how they use the tool, what actually they're looking for. And if we can just, prioritize them as opposed to, here is the exact right one, I think that's a huge value add in terms of like how we go from, proof of concept of like, it can do this roughly to actually narrowing down the business case and narrowing down, what the tool is actually doing to like industrialize and productionizing. So that, like really that's that journey of like expanding the scope as you go. And the last phase, and I'll end my monologue I think on this little section, is really that operate step. And I'll give you a separate example here in the operate space. So this is where you actually get this thing now to tens of thousands of users, and you're like maintaining the system live, right? And this is probably one of the hardest pieces is moving into this operate phase because like actually developing the technical solution for the most part, it's relatively easy. It's that human and the data drift and all this other stuff, like that devil is in the details right there of like actually managing the system. And one of the big things that we've we've seen is that if your human users don't believe in the tool or like they won't use it. And one of the huge anecdotes that I saw over the last few years is I think it was like diagnostic for medicine of like cancer or no cancer, and the humans were like 70% predictive or 70% accurate, and the AI tool was like 85%. It was like markedly better. But when the like physicians were given the AI tool, they were like combined 60% or something. So they're combined worse than either the humans or the AI separately. And it's because the physicians were like so disbelieving of what the AI is recommending, is that they like, no, that's not it. And like they basically just ignored it and actually went against it. And like that happens all the time. And so like one of the big things of scaling and operating these systems is making sure that what we call change management and change is managed. So people like can understand the tool, what it's doing, and being brought along for the ride. In the client that we're serving right now, this sort of manifests uh, in a weird sort of like the older generation of people who've been at these companies for like 20 years. They can identify the part number from a vague description, and it's like I know this 20-digit SKU number based on like this arbitrary string of like letters. And it's like okay, that's like savant like, but which is amazing. But they have a hard time using this tool now because like if they can do that, which is all internalized in their brain with the pattern recognition, it's like, why would they use our tool? And we have to like walk them through why our tool is slightly better. It has a lot more information around, margins or like, profitability of each item, where each item is in stock versus out of stock. Maybe they're even recommending slightly different items that, might not actually be the best fit because, they're familiar with the, subset of things that our client is selling, right? And so like trying to convince people who've been there 20 years doing the same thing of a new thing is absolutely the hardest part of building any Gen AI solution. And sort of like the one thing I wanted to touch on as we do this. And like I'm a physicist by training, and I tend to like sticking on the technology side. The technology is again conceptually relatively easy. Like I can tell you roughly a solution or not in a day or two. It's like that human aspect of it that, especially in the Gen AI space, is hugely painful, but super important to get right. And so I think that was the only thing I'll hammer home on this slide. Okay, I have two more slides on talent, and then I will hand it over to Alexis around more like functional stuff and less, business consulting thing, which I've sort of been invested with the last 2 years. So talent. So as I was mentioning, the huge like change management of how clients or how like people or organizations are like accepting and using tools is a big deal. And in organizations are thinking about, what are the type of people that we need to hire and manage and upskill? What are the type of skills they need? If you move to the next slide, Alexis, what are the types of skills people need? And if you just look at across like the overall sort of, proof of concept to delivery and operate, the advised to operate framework that we have, like you can think about the types of people you need, like the solutions architect, engineers that know how to hook up data and like govern it well, people who manage the risk, UX developers, people who understand the Gen AI technologies, data scientists, and as you guys are looking at building your own careers and professions, like all of these are critically important across the board. And so as you sort of like span the gap from the start of like an idea from an AI strategist point of view all the way into like actually getting your hands dirty, hopefully in the next 30 minutes or so, like there's a ton of different opportunities and a ton of different skill sets that you can take your career down, and you can be a specialist in any of these things. except maybe prompt engineering, which is I think my only other point here. I think last year, maybe the year before, like prompt engineering was maybe thrown around as potentially a new career trajectory. I think it's sort of been dispelled these days, but I think a lot of prompt engineering is, first of all, I think, in my opinion, like a limitation of the algorithm. Like I think like it being dependent on your prompt as opposed to like your desire for like or your intuition. I think that's a big failure of the modeling perspective, right? I think it's not actually necessary. So I think that's one of them is just the current limitation of prompts. And I think as we'll go, it's going to be easier and easier to prompt things, and the frameworks and how you prompt is going to change as well. But I think that's the current limitation that exists as opposed to an actual profession, in my humble opinion. If this proves to be one of the most lucrative careers, then maybe I'm wrong. What instead I see is prompting becomes sort of inherent in like the job that you do. Like you'll be able to like everyone can Google search, right? It'd be like that kind of level of complexity where yes, maybe some people are slightly better at Google search, like I'm better than my parents at it. But I think the like a baseline in terms of like how it enables your workflow specifically, or like how you are a better software engineer with it, will become a thing. And so just highlighting here just the different roles and as we see it, technical aspects required for roles that for the most that we see. But that's basically it. I just wanted to mention that, you know, I love all of aspects around the talent perspective and talent journey, just because like I've seen personally like how AI has shaped my personal career and then the careers of people that we've hired and sort of developed over time. Um, anyway, that was hopefully a good summary of how the organizations out there are sort of like attacking um, the more strategy and development of things at a high level.
I'll
With that monologue done, I'm happy to answer questions around any of that in the chat. Otherwise, Alexis will give you actually more functional, useful information than just the chat.
So
I will
we
ride on Mike's coattails there a little bit. So, you know, relatively speaking, I am fairly new off the job market and coming from academia, learning the technical side of things was, I mean, it's definitely not easy and it's definitely, you know, it feels ambitious to start something completely new. But to be honest, it's a relatively new field, so things are somewhat accessible. It's still like you can still become an expert in these fields. Now, but the content that Mike just delivered in terms of the actual application and doing these things, that takes a little bit of time to actually like get a grasp of. So it is really nice to have that insight, especially a career move if you are looking to get into the AI space. Like, how do you actually, and you'll get questions like this on an interview. Like, what does it actually look like? Like, if this is a problem statement, like, what would your approach be? Start small, prove out feasibility, get big. Like, all of these ideas and these concepts, they're not just like these high level ideas. Like, they're actual practical applications that happen. So at this time, we'll probably
I
open
have
up a
a few
little
more
bit of
slides
time
actually,
for some
Alexis.
Q&A.
Don't I?
So
Alexis?
there is in the do you want me to read it out, or I'm happy for one of you to read it out, which
Oh, I can answer that. So first of all, I think there's no substitute to getting your hands dirty. And by getting your hands dirty, I mean beyond what's on Kaggle. Kaggle is great for like learning the modeling and learning like the core algorithms, perhaps. But real world is the 99% data wrangling and the mess of free-form data. So I would almost like set up your own web scraper, pull data in, and do some sum and build something that's like independent of like a very nicely bound problem, right? And I think that's probably my perspective around like how do you get hands on keyboards um, practice. I think in terms of like books and those kind of things, like yes, depends on where you are in the journey. Like obviously, join Brown's data science group and master's program and all that stuff. In terms of books, my favorite for a holistic overview is I think it's called like ML Engineering by Burkov. Borkov. That one's like really good in terms of just like running you through from end to end. And then like the traditional courses you see out there for deep learning and AI, I think those are obviously very good. Separately, I think my personal favorite, just as myself, is the Fast AI one, which I like to advertise. That one's run by some professor, I can't remember where, but that one's really good. That's very hands-on keyboard functional. Sort of like if you were looking for like an online resource, I think that one's the one I like to advocate for.
I can add what I used as well. I strongly focused in the beginning on Coursera courses. It's kind of how I got my initial start. Well, I should say my initial start was that a student approached me wanting to do a machine learning problem where he wanted to use a deep learning neural network to draft his fantasy football team. And so it was kind of like, I'm going to tell him I know how to do it because I've heard of it. And then I just need to be ahead of him. Hopefully he doesn't watch this. And so essentially I just kind of started learning neural networks, and he won his fantasy football that year. And I was like, all right, cool, I'm a data scientist. But realistically, I think that kind of goes around what Mike's point was. Okay, there was this problem, there was an end goal, but like the data wasn't necessarily just handed to us on a silver platter. We had to find that data. So think of a big problem, like maybe something like you want to beat these sports gambling websites. How can you develop a predictive model that actually says where you should place bets, when you should place bets, something like that. And so these problems that would actually require you to see a holistic solution, do all of the data wrangling and cleaning on your own, and actually create the entire pipeline yourself. I think that's more valuable than anything. Of course, you do need the basic foundation from some of the courses that you might do. And then when it comes to when you like get to the very end stage and it comes to like interview prep, there's a really nice book. It's red. I don't remember the name exactly, but it's like Preparing for Your Data Science Interview. That's a really nice book in terms of not depth, but breadth. It gives it was before Gen AI, so it will probably, at least the one that I was using, be a little bit limited. But it does cover like, okay, here are the types of questions you might be asked. Here's a behavioral interview section. And then like the technical section is like, okay, here's some concepts that you should be familiar with. I liked that. And then there was a boot camp held by Erdos Institute, ERDOS. They truly do just work with PhDs and postdocs or people coming from academia and wanting to transition into industry. So look them up. Potentially, they were a great resource for me. So.
Yeah. And I think also, so building the models and scraping the data, and then also validating and making sure that that is bulletproof. Um, because I think what happens is like, especially in Gen AI, it's like it's kind of arbitrary and like, it kind of works and doesn't. But getting some quantifiable benchmarks and metrics behind it is super important for like, any type of progress of like, otherwise it's just shooting blind in terms of getting improved solutions. I actually forgot that I had to have a few more slides.
There's another good question for Mike in the chat though. As someone in a position to hire, I'm curious how you think about how a physics PhD with some experience in ML can compete on the job market with candidates with more in-depth experience.
So, I mean, I'm biased because I come from the same background. I don't think we have any fully data science PhDs on our team. Like we're all STEM PhDs. I would say like more than half our team are PhDs, and almost all of them are STEM. I think it's really that fundamental, like being able to problem solve, being able to adapt to situations and create a solution, and then especially like rigorously validate it and vet it, and make sure that your reasoning is accurate and like all that stuff. I think that that's where we differentiate. Like the AI and deep learning and like those people, for the most part, I would say like their research and their level of competency is more towards like the fundamental stuff, right? It's not really um, like what I see is like again because we're more of consulting and more applied data science, I'd call it. Like we see a lot of like all our companies that we see, are basically needing the type of people that are more functional and more like broad and be able to problem solve, as opposed to, we need to optimize this particular model to 99.9%. There are obviously jobs like that in the high-end R&D places, and like if you're really trying to eke out that last like 1 or 2%. But in most organizations that we ever talk to, and again, it's selection bias because we only talk to people who don't have it. Like I would say 99% of organizations out there require data scientists that actually aren't for that like top 1% of solutions, but really like how do we have a thing that's well balanced in terms of cost, accuracy, implementability, and like be able to actually deliver to users that use it, right? And so I think that's really the lens I would put on it. Wanted to cover a few more industry applications around just sort of the things we've worked on and things you've seen. We like this slide because it's covers not just the LLM piece that everyone sees obviously these days. We work for a large, and this is a European nuclear power company. They basically had to organize fuel rods in such a way to optimize, power output without obviously blowing up everything. But then also like they have different ages of the fuel rods, so like they have different power outputs, and they have like all these configurations you can put them in. And like historically, what happens is like some engineer that's been there 20 years says, we should put that one in fuel cell 17 or something. Right? And the configuration and the exact geometry is like an NP hard problem of like how do we actually put all these things with like all these different attributes around fuel cells and fuel rods and like their composition and their age and their like whatever, and like how do we actually generate a pattern that would make the most power output for the fuel rods that we have, right? And so that was the problem statement. We created a simple GAN to basically like recommend new fuel rod configurations, and then we had it basically train against some of like the harder constraints and some like simulation um, data of like, if the fuel rods look like this, like there's some programs out there that like can estimate the predictive power output, those kind of things. So like that was a really cool one because it's completely novel and you don't really think about it this way. I'm also kind of worried about just the whole industry and nuclear power and everything blowing up, but that's a separate side quest. Again, I think it's just a huge avenue where you don't think about it, and there's a lot of applications for GenAI. Second one is teledentistry. This is one of my favorite in that it was kind of like a weird. I love the weird projects. This one was like a, a big, like this is like billion-dollar company, wanted to scan your teeth, and instead of like having to go to a CVS or Walgreens or whatever to scan it in like like a dentist place, an orthodontist place, they would basically just take 3 or 4 cell phone images of your teeth and be able to go from cell phone images directly to like a 3D representation of your teeth and send you out a mold and send you out like braces, right? And so like that was the problem statement. We got it to like pretty good accuracy actually, and it was like kind of crazy, but it was like that 2D to 3D generation. Again, there's no open source model for this or even closed source model for this, and we basically had to build it from scratch. Pretty cool. We saw a lot of teeth. I think a couple of our people who are still around in our company got their teeth scanned for free. So they have like molds of their teeth and all that stuff. Again, pretty cool to have a digital file of your teeth. The last one is more traditional LLM based. This one we've actually done a lot for clients, and the last 2 years it being all about chatbots and those kind of things. Be able to assist in sales, sort of the sales journey for companies. So for this case, it was more of a large confectionery seller. You'll know the name if we told you, but basically they were looking for an ability to augment their sales associates to like sell to the Whole Foods or Walgreens or whatever. They're selling their products to these people, and they sell them in bulk, right? And so the idea here was to like generate sales pitch decks that were like 100 slides long of like the types of products and why they matter to that particular account. So Walgreens would get a particular deck about these types of goods, and they would be tailored towards like, oh, Walgreens is more interested in plastic consumption and making sure that's reduced, right? And so like having that layered into the sort of like the pitch and like, oh, this is 10% more effective with packaging or something, right? And so be able to do that at scale. And then again with some measurable metrics behind of like, if you do this, it's like 10% better or 20% better in terms of like, historic sales, right? And so again, that's where we see a lot of the stuff, especially in the retail consumer product space, around the Gen AI, like I would say the last 6-12 months. I'm going to skip this one actually. But basically, I think the core challenges in AI is defining the problem. That is probably the hardest thing to do, is like you have to narrow down a problem that's solvable, right? And once you do that, like a lot of the other solutioning is, in my opinion, relatively easy. It's like just getting consensus of like what the problem is that you want to solve and why, and like the business value and all that stuff. Once you get that, like it's like, oh, if you learn the algorithms well enough, it's like this type of algorithm that solves it, right? As long as you can nail down the right problem. Yeah, and the other like data representative and stuff like that, it's hopefully well known. Okay, this is definitely the last slide for me. So I just wanted to splash this up there. Effectively, as you're learning the technologies and tools like RAG or React or agent stuff that we're going to talk about, it's just core that the technologies you learn are applicable in any industry. And so we actually do work on very similar engagements from the technology perspective, but apply it to basically every company out there. So like that sales bot I told you about, like that bot that's everywhere, right? And that's everyone needs to sell some things. That's what we do. The nuclear power rods, maybe not quite, but there are other things that need the same type of, manufacturing. And in the manufacturing space, that's like obviously a big thing, right? Like shelf optimization, for like, even just shelves, warehouse shelf space, right? How, like what configuration to do it so that the load is like, I don't know what it is, but like that kind of technology around GANs and neural nets, again, fundamental across the board, right? And so if you learn the technologies really well, you can basically see the patterns everywhere in terms of like where these apply to. The other one, last example I'll leave you with, which is my current favorite, is 2D to 3D modeling. So the teeth one is the one example. The other one we had was in 3D modeling towards like LiDAR and like detecting tree growth and trees getting near power lines. And so we had this huge energy company somewhere in the US, again, nameless, that basically gets fined by the government for trees that encroach on power lines, because obviously they have like wildfires and issues around like safety for the public. And so they get fined like millions of dollars a day per incident of a tree growing too close to a power line. And so like the use case there was to first predict tree growth in 6 months, so that, and trees grow at different rates, but tree growth in 6 months, if they will encroach on the power lines, right? And like we used some LiDAR data, we used some satellite imagery, and I think the key nugget that I really liked here was like we had this weird data issue, and this goes back to like data being a big problem. Weird data issue of like we couldn't quite get the coordinate systems to match for where the trees were and the satellite images. And it turns out that the LiDAR images that we take from like drones and helicopters were on the tectonic coordinate system. So like on a plate, on like tectonic plate, and they would move like a couple inches a year, obviously, and it would be out of sync with like a geospatial, like the GPS system. And so it took us like a month of scratching our head, like what the hell's going on? It's like obviously the 6 inches of our error tolerance was like, oh, it's kind of weird that this never matches up, and like it screwed us over for yeah, quite a while. And so like those kind of nuggets, I love them, but again, they happen everywhere. And so that's the kind of problem that you'll see in applying the technologies across the board. Okay, that's it for me, for sure.
All right, sweet. Thanks, Mike. All right, I'll keep an eye out to see if there are any other questions. At this point, this is when we'll move into a little bit more of the actual technical content. The first thing we're going to do is we're going to talk a bit about development of large language models, starting with the evolution of NLP. All of this is super new. The space is, at least relatively, when we're speaking from someone who came from doing math in an area of research that, started in the, 60s, and that was a relatively new branch of mathematics. This is far beyond, like, this is way newer than this, anything where I've ever, was ever used to before. So the evolution of NLP, or natural language processing. So I just like this graphic where you're going to kind of talk about the pace of advancement of Gen AI. And I think it's a really just awesome slide in the sense of, okay, in October of 22, if you asked an image generation model to generate an otter on an airplane using Wi-Fi, this is what you got. They were probably super impressed by it at the time. And now in May of 2023, you get an actual image of a pretty realistic looking otter using a computer on a plane, and like there's a jacket behind him. And then in February of 2024, we get something where if we test the prompt Labrador hacker, we can get, we can generate a video of a Labrador using a computer. So just to show that, from October 2022 to February 2024, that's the kind of advancement we were seeing. I think it's just, it's pretty incredible. And to be in the space, that just goes to show, there's a lot to learn, but there's a lot of people working on it, but it's definitely accessible for everyone right now. All right. Again, you can kind of see the evolution where we start in 1950 with Alan Turing running some tests for machine intelligence, and now bring us, I guess, 73 years. 1950 doesn't seem that long, but it is. And we just see the evolution of, these large language models and Gen AI, just machine learning in general, and how quick it's happening. It's like 2014 was the first Alexa. That's, just 10 years ago about. Okay, again, we see the evolution now starting down here. I like this. We're going to start. This is the things that I'm actually going to talk about, which are this thing called word to vec, or GLOVE. This is a method of embedding words in some space, and we'll talk about what that actually means. And, that was back, like 2013. And now we get back, we work our way through some of these more sophisticated embedding models, and we talk about BERT, which is another embedding model. And then we work our way out for the tree, where there's just these large language models, and there's this nice fancy phrasing of encoder only, encoder decoder, decoder only. We're not going to touch on that right now. I'm going to I don't want to get too deep in the technical details, but these are things that I want to introduce you to, that you can actually, these are phrases you can look up, things you should be familiar with if you are interested in learning and getting into the space. All right, so where I started when I was doing NLP was learning how to actually vectorize sentences. So, a computer itself doesn't actually read the text, but it sees sequences of numbers, right? So we're going to start with just the most naive, basic approach to vectorizing text. And you'd be surprised at what kind of models you can get using this approach. This approach can work relatively well for a lot of different classification tasks and things of that nature. Oops, I did that to Mike as well. And so what we see here is something called count vectorization. And what I did was, we have a sentence and we have a list of words. And this list of words is this bag of words. It's our vocabulary. It can be whatever list you determine captures the meaning of what's called the corpus, or like the group of text that you're interested in embedding. And what we do is we just go through, and if I see a word, I go ahead and I put a 1 in this. We can think of this entire thing as a vector, and a vector representation of this sentence. And so the word she shows up, I put a 1 there. The word love shows up, I put a 1 there. The word math shows up, I put a 1 there. Put a math shows up again, I put a 2. This is where the count part comes in. Is a 1, the a 1, coolest a 1. Everything else gets a 0. So she loves math, math is the coolest. Same thing for this next sentence. She loves physics, physics is the second best. And so we vectorize that sentence. And then she is a good person. We vectorize that sentence by doing the same thing. A 1 under she, a 1 under a 1 under is a good person. Okay, so if you were to just cover up that left-hand side and you were to kind of do an examination and you wanted to know like what were the most semantically similar sentences, which ones had the most similar meaning, you could actually look at the vectorization, and ones that have more common values are more similar. And if you've used linear algebra recently, you know how to compute something like that. And so to find out whether or not two things are similar, what we do is we multiply component wise. So 1 times 1, 1 times 1, 0 times 2, 1 times 1, 1 times 0. We add all of those together and then divide by the length. And we get some sort of vector, some sort of number where if it's higher, it means that more of these things were in common. And if it's lower, then there were less of these values in common, meaning there were less words in common between the two sentences. And we can use that to capture somewhat meaning of a sentence. Now, there are more sophisticated approaches to doing this. The first step up is something called TF-IDF vectorization, where we actually take into account like word frequency in the entire corpus or your grouping of documents. And we do something where we kind of TF-IDF, you kind of like scale out by that frequency, but regardless, it all works somewhat the same. Okay, but downfalls of this, you can probably think of a few. If you're only counting words or like looking at the occurrence of words, and you could rearrange the sentence, it would have completely different meaning, and you would but like your vectorization would look the same. So if you think about like product reviews or something, let's say you want to say this product is the, crap, whatever, the word. But if you rearrange this, like that's a good thing. But if you rearranged it to say like this product is crap, then like it's a bad thing. Problem is like those have basically the same words, two really different meanings, but we miss capturing meaning, or we miss the reflection. The order isn't reflected in this method. So there's your downfall. Again, plenty of tasks like this is very basic, very easy, relatively low compute when it comes to actually doing the vectorization. So like a great method, actually, it's surprisingly well. Okay, but we soup it up a bit. Now we can talk about actually vectorizing words in terms of capturing their meaning. And when I say that, what I mean is we can train these, okay, let's see, like word to vec is one of the first vectorizations of words that actually captures their meaning. And we train this vectorization in a couple different ways. There's a couple different methods. We have CBOW, where you actually try to predict the next word, and that's how that's trained, or skipgram, where you like take out a single word in the middle and you kind of predict the word that's missing. And that's how these things are trained. Now, I'm not going to go into the details. Again, we're skipping a lot of the technical things that would take kind of a while to explain, but I want to capture the actual implications of these. And so we have projected down to 2D space. These vectorizations, they are in a much larger dimension, but in 2D, you can see if we were to look at these groupings and where they are in the space, they have relatively the same meaning. So, if this is a point in space where boy and daughter and son, there's a point in space where these are embedded, things that are embedded close to one another have similar meaning. Great, that's kind of the goal. We wanted to be able to embed words and have their meaning. If you talk about a sentence, you can actually average over the word embeddings and get a relatively good embedding for the sentence. That also works surprisingly well. Okay, so there's also a really cool phenomena that was not necessarily expected. And that was, okay, let's say, for example, that we can look and we can see where king is. And then we know where man is and we know where woman is. Well, if you were to look at the vector that takes you from man to woman, and you place that vector, the base at king, you'll get to queen. So that means, like, if you took the vector of woman, subtracted the vector of man, then if you added that, like, resultant vector to king, let's hope I did it the right order when I said it out loud, then you would get the point or the vector, at least really close to the vector of queen, which I think it was a really cool result. So long story short, there are these dense or continuous vectorizations where you actually, the vector is no longer just this one hot encoded vector, but it's a they're all real numbers. There's no zero values, and you're embedded in this large space. All right. So, my apologies. Now, just kind of giving you a little bit of the flavor and the story. So now, how do large language models work under the hood? Well, at the very core, they rely on these vectorizations. And then as these large language models, if we're talking at the point of when they're actually doing their generation, is, okay, we take into account previous things, and then we also take into account the current generation. And all of these have different embeddings, and I'm going to be very loose here, but what happens is those are used to compute, okay, we want to know what word's going to show up next. Well, all of those get passed through some sort of network to give you a distribution, and depending on the parameters that you choose, a distribution of potential words that would pop up next. So I'm tired, I need some. If we're not taking into account any other context, and that's all we just take into account what's already been spit out, okay, you get a potential distribution of what the next words are. And then the model chooses from that distribution using different parameters. It may just choose the highest always, maybe because you have temperature set to 0, or temperature is set to a little more than 0, so it might consider a few more with some sort of distribution. And so that's how you would use to, and it would pick this next word, which is I need some rest. Okay. And so that's how this generation works in large language models. Okay, cool. And so, transparently, like, a lot of what we do is not necessarily, we're not developing new large language models. We're using them in a lot of cases, we're doing a lot of RAG. And so RAG, which is retrieval augmented generation. And so you heard a talk from James. So again, I'm going to kind of gloss over this. We want to get to the notebooks. But retrieval augmented generation is a technique in the field of natural language processing that combines retrieval-based and generation-based approaches to improve the performance of large language models, particularly for tasks such as question answering, information retrieval, and text generation. Okay, so that's the text on the slide. What does it actually mean? Well, okay, I'm going to skip ahead to a slide real quick, but what we do is we take it's a retrieval step. So based on what you're given, we're going to go ahead and we're going to, I lied, I don't want to go there yet, but we're going to go ahead and we're going to find the relevant context based on what you asked. So anything similar to what you asked that's in this context available, you're going to pull that back. You're going to use that as text. And then you're going to actually use that context and ask the large language model to use that context to generate a response. And so why is RAG important? Well, a lot of these available large language models are trained at some point in time. And that point in time is not now. It may be a couple years ago. And so if you're asking and you want to be able to ask about content that's available now, well, we need the large language model to have access to now. And we can use retrieval to allow it to retrieve that context that you need so that it can answer questions about things that happen in real time. Another example would be maybe you have a client or you're working on a project where you need access to proprietary data that maybe the model wasn't trained on. And you can use this retrieval architecture or this RAG architecture and retrieval to gather that information that the model didn't have access to when it was trained, and actually generate a response and use that information. Okay. And so there's some nice advantages to RAG listed here, maybe a few outside of what I just mentioned. And then this here is an architecture diagram for retrieval, for RAG, I should say. And all right, so I'm going to pause and I'm going to allow you to digest this for just a second. But I want to mention that so the non-dashed arrows, they represent something that happens in like the back end. This happens before inference time. So what we do is we take this raw data. So any data that you would like the model to have access to, and we embed it. So that embedding we just talked about, well, we embed that data. A little more complicated, there are sentences and things like that. We're using some sort of embedding model to embed that data. Once it's embedded, it gets stored in a vector store. All right, so what does that mean? What is a vector store? Well, a vector store is what ties together those embeddings together with more information about what you embedded. So the actual content itself. It's important that that embedding gets tied back to your text. Okay, you also might have some metadata saved along with that data. So for example, maybe I'm embedding information about some sort of from a rule book. Okay, well, maybe I embed text, but in that metadata, I want to store the rule number that it's associated to. That can be stored in that metadata. All that would be stored in this vector store. Okay, so then the dashed arrows are what happens at retrieval, at inference time. So at inference time, what happens? You already have your vector store, which is all of the embeddings from the context. It has these vectors paired with the contents themselves. And what I can do is, what happens at inference times, a user develops a prompt. That's some question, it's some phrase, whatever it may be. That prompt itself gets fed to the embedding model. That's step one. So that prompt gets embedded. Okay, once that prompt is embedded, we do a similarity search. And so what is that similarity search? That similarity search is something that's really similar to what we just talked about, where that similarity search looks in the space. So here's your, let's pretend we're just in 3D. This can is my query, and other points in this space are embedded documents in this vector store. Okay, when they're going to take the ones that are the closest to it. Those closest documents in our vector store, I should say vectors in our vector store, are the ones that are considered the most similar. And those are the ones that will get back as retrieved context. So user query, embedded, get all the most similar contents, and that's your retrieved context. Perfect, so that's the retrieval step. What happens after the retrieval step is both that context together with the prompt get fed to the language model. So you combine them, the augmentation step, and then they get fed to the large language model. Okay, and then in that large language model, they then, that's where your generation step happens, and you generate an output based on that augmented context together with your prompt. All right, awesome. So there are a lot of, this is the most traditional RAG architecture. There are other things that you can do, especially with agentic workflows that do things like send that prompt off first to get enhanced, to have it be in a better form to do the retrieval, things like that. There are plenty of other enhancements you can make to this, but this is the retrieval architecture at its most basic form. Okay. And I'm actually just going to skip that. So I'm going to ask, are there any questions? And if there are not, we are going to pull up our first notebook for module 7. And that first notebook is part 1, embeddings, vectors, or embeddings, vector DBs, and of course I don't remember what I named it. And RAG.
Part 1 is also very useful.
Yes, part 1. And I am going to switch over to sharing screen from another laptop. So just a second. All right. So while you're getting that pulled up, I'm just going to talk through the overview of what we're going to do. First thing we're going to do is we're going to go through this part 1. This part 1 walks through RAG, and it will show you everything that's happening inside of all of the large language model calls and what the RAG architecture looks like from start to finish. And this is, quite frankly, very, very similar to a lot of the RAG architecture work that we do. Boots on the ground, like this is it. So yes, there are enhancements we do, but this is an actual implementation of RAG architecture, just like we walked through. So I'm personally not going to run the notebooks in real time for several reasons. One, they're a little bit slower at times. Two, the large language models don't always have exactly the same output, which you've recognized. We are going to be using a smaller llama model that will require you to download that here. And so some of this takes time, some of it I've done ahead of time, but I'm going to walk through the notebooks and I will take my time. Please, please, please feel free to run them on your own or just follow along. I want to have these for you as a reference both later and now. I do have I have a version of this notebook that does run locally in Jupyter Notebooks, not in Google Colab. So if that's something you're interested in, please feel free to reach out for that. Otherwise, for now, we're just going to run it through Google Colab and get off to the races. All right. So let's see. Okay, cool. So the first thing we're going to do is, along with that Google Colab notebook, there were some other files that we have saved. One is a requirements file that lays out all of the installations that you'll need and the packages, the Python packages you'll need to run this. And then this Colab Xterm, there's a functionality where you'll actually need to bring up a terminal inside Colab. So running that will go ahead and run all of your installations and connect you to your Google Drive. Please, you may need to change this Google Drive path depending on if you have this connected in your shared drives. Great. All right. So the first section we'll talk about is embeddings. And there are many, many, many embedding models. You can also fine-tune embedding models to be developed for a specific task that you have. Maybe there's a corpus of text or things that you're looking to embed that have some weird words in it. Those would at times be embedded as like unknown tokens, but maybe you have a lot of them in your context and you want the model to actually learn what that unknown token is and learn an embedding for it. So you could fine tune a model. For today, we are going to use this open source GPT for all embeddings. There are also, I should mention, embedding models that have been trained for particular tasks. So if you're looking at working in a particular industry, you can look at different embedding models. You can even just go on Hugging Face. There's a website called Hugging Face, and you can look at the model offerings there. So we download the embedding model. The first thing we do is I develop a test string. That's test string 1. You can put whatever text you want there. And what we do is we call the embedding model and we embed the query. And that query is whatever I defined as test string 1. Okay, so I run that and I embed it. Running this next cell will actually print that vector. And so you can actually see what that vector is. And that vector is this nice well, it's an array or a vector. And okay, how many entries does it have? It has 384 entries. So this is a point in 384 dimensional space. All right. So here we maybe embed a new test string, and I can embed that new text string using the embedding model by running this cell here. In doing so, I see I get another vector. Okay, that vector has various different entries for each of the 384 coordinates, but it also has length 384. This is a really important thing. If you use the same embedding model, you should definitely get the same length vector, because to compute how similar two vectors are, well, we want to know how close they are in space. And closeness is defined by using cosine similarity metric usually. And if you take a few minutes or a few moments just to think about why you'd want to use the cosine similarity, well, if you were to do Euclidean metric, that would be higher compute, right? You'd have to like take the difference of all of the different components, then you'd have to square that difference, and then you'd have to add all of that up, and then you'd have to square root it all. You could avoid the square root because, okay, if you're just interested in relative distances between two things, you would need to square root everything. It would be the same, but that being said, like that's more compute than just multiplying all of the components together and adding it all up. Did I see, was there anything in the chat that I missed? Are we okay so far?
Okay, I was just adding a bit of advice to people who are, if they are trying to run the code.
Got it. Sweet.
And running experience. Please, sorry, Alex, I didn't mean to interrupt you. Just wanted to make sure they understood about the nuances.
No worries. Please interrupt anytime. We have, plenty of time, plenty of content. If we don't get to it all, I'm happy to share the notebooks, and really they have the notebooks, and hopefully they're well enough documented and can shoot me some emails if not. So we use cosine similarity to determine how close two vectors are. And so otherwise, a dot product. And so that dot product, because all you're doing is multiplying all the components and adding them all together, because these vectors are normalized, meaning they have a length 1, so you just be dividing by 1. And you'll get a similarity score. Okay, so if you recall from back in your linear algebra days, or you use this as your recollection, things with higher similarity score are so a similarity score closer to 1 means the vectors were closer. A similarity score of 0 would mean that they're extremely far away, closer to 0, I should say. So this dot product will always be between 0 and 1. The higher number, meaning the vectors are closer or more similar, the phrases are more similar to one another, and a lower number closer to 0 in this case will be that they are further away or the more dissimilar. Okay. Great. So I encourage you to just kind of change these strings and change them to Alexis likes dogs and something else that's wildly different from that statement, such as there's a hamburger on the street, and look at those changes versus there's pizza on the road and there's a hamburger on the street, and try those similarities, and you kind of play around and you'll see that how these embedding models actually do in fact encode. My apologies. So okay, cool. So we've got the first step of creating a vector database. We have the actual embedding itself. This next step is we're going to actually create a vector database. And so there are a lot of different options for your vector store. One of the nice and easy options to run locally on your computer is something called Chroma DB. And Chroma DB is an offering for a vector store, and we are going to use the LangChain wrapper around Chroma. So LangChain has essentially provided a framework. It's a company that has provided a framework for a lot of the generative AI solutions. And they allow you to use different models, and they're attempting to make it very seamless to pop different model offerings in and out, pop different embedding models in and out, swap out your vector stores, and all of the implementations should be relatively similar using LangChain, or they're now moving over to LangGraph, I believe. But there's my little plug for that. So we do use LangChain implementations. It's a little more seamless. All right, so what you're going to do is you're going to create a path to where your vector store will lie. I have this config file, which is located in the drive, and that config file just contains some vector directory path. It was easier. It was a little. This is nice to have these environment variables, or variables, I should say, that are consistent throughout your notebook to be stored somewhere else, so you don't have to worry about defining them anywhere. And you get to make sure that they're consistent if you have different files and different notebooks and things like that. Okay, so if the path to the vector store doesn't exist, create it. And if it does, then we will just load it itself. And then this cell here, okay, we name our vector database. This is for this sample vector database. I'm going to label it as basic physics. And this basic physics vector database is going to be, okay, so here's our Chroma instance. This is where we're instantiating it. We use our embedding model, which, if you remember, we defined to be up here, this GPT for all embeddings. We made an instance of this GPT for all embeddings. Okay. For what it's worth, my scrolling is opposite on each of these computers, so I apologize if I'm making anyone sick. I'm making myself sick. Okay, so we have this persist directory, and that is because we want this vector database to stay around. I want you to be able to access it later as the same vector DB. If you don't include a persist directory here, your vector database will be here during your instance of while you have this running, and it will go away otherwise, which at times we use that as well. For example, if I create a tool where I just want to really quick do some RAG really quick, I'll create a vector database that just like sticks around in the app. They use it. Once they close out of the tool, that vector database just goes away. But then there are other times where I want a vector database to stick around. For example, maybe I have product information stored in a vector database that everyone needs access to all of the time. That's created, it sticks around, it's created way before they're actually using the tool. Okay. Now this collection data metadata, this just specifies to Chroma that we are using a cosine metric for computing our similarities. So it is going to tell you that Chroma when you're doing the embedding, just in case, it normalizes everything, and it knows when we're doing the similarity score to use a cosine metric. There are other offerings that you can put there, and I just wanted you to see that. Okay, so now we have text that we're going to embed in our vector DB. And here, for just ease of looking, we have embedded some basic physics terms. So I say physics. This is like high school physics, probably where I stopped. And so we've got gravity, force, velocity, acceleration, momentum, energy, work, power, friction. And I just looked and I embedded the word together with its definition. So to actually do the embedding, what did I do? I said vectordb.add text, and this did it all at once. So what it did is it called on this embedding model or embedding function. it used it to embed the text. And if you remember the graphic, what happened is it put it into that big bucket or that vector database, that cylinder. All right. So it did the embedding and then it stored it and it indexed it. So it paired the text together with its vectorization. Okay, all right, weird. What do I see here? I see these like really long strings of numbers and letters. That makes no sense. I didn't see one of those when I did embeddings. Well, this hash is what's used as an ID. It's a unique identifier for the text and for the embeddings themselves to kind of tie them all together. It's your hash key. Okay, so this just tells me everything was successfully embedded and here were the hashes that we used. Okay, so how do I actually use my vector DB? Well, okay, there's this just method called similarity search. And if I take my instance of my vector DB, remember that vector DB is set to be equal to the instance of chroma. I embedded the text, so you can think of this vector DB as this big cylinder. And I do dot similarity search, what is gravity? So what happens is all in one, my query, what is gravity, gets embedded as a vector. So now the vector DB says, okay, I have your query. It's a point in this space, 384 dimensional, if I remember correctly, based on our embedding function. And then it says, okay, I have all these other vectors stored in my cylinder, my vector DB. And I'm going to look at what are the most closest ones around it. I think the default was 4 on chroma when you do this similarity search. And so it pulled and it looked at what were the 4 closest vectors in that space. And then it went and it pulled that content. So I have no metadata saved. So I didn't really bother, didn't save anything about these things. But I did, and I did pull them closest content. These were the strings that were embedded. And lo and behold, gravity is the first. Force is the second, work is the third, and momentum is the fourth. All right, but okay, that doesn't give me a whole lot of information because I don't know like how close they were. But okay, we can also do something called similarity search with relevance scores. And what that will do is it will actually pull back the closest together with the score for how similar they were. And so you'll notice when I do this, retrieval only, right? We're not generating anything. We've just used our vector database to do that retrieval. So that top rectangle that I showed in my slides. So this is where I will pause and ask if there are any questions. I see a couple open. Yeah, okay, so yes, someone asked about cosine similarity, and yes, that does actually range between -1 and 1. There's some normalization that happens to make it between 0 and 1. Or I shouldn't say normalization, but some scaling factors. Hopefully that answers your question. I will be talking a little bit loosely because I don't want to get like bogged down with the mathematics. But it's kind of used, it's a bit of a convention that we like for things to be between 0 and 1. Okay. So you can test it, and then we can set things like K or a score threshold. And so if I look for the word test, so I do similarity search with relevant score, I set K to be 3, meaning I want to retrieve at most 3 documents, or a score threshold of 0.4. And I got back that no documents were retrieved with a score threshold of 0.4. So there was nothing that was similar enough to the word, the phrase test to be retrieved. Now, I would encourage you to replace that test string with something that may be a little more relevant and play around with the score thresholds and your K value. A lot of what's done when we use RAG architectures in industry, we want to make sure that what's being returned is actually relevant. But relevant and that score are often determined by, We do some data science. Like we actually take a large sample set, we range what these K values are, or we range the score threshold probably more realistically to make sure that what is actually returned is relevant. But again, that threshold determines that is very much dependent on the task at hand. Okay, so some other nice convenient functions that we have are the .get function. These are kind of particular to Chroma to a degree, but I did want to show you because sometimes they are nice to use. And so if I use my vector DB and I say .get and I say include documents, metadata, embeddings, okay, it gives me back what's called a dictionary. And the key value, the keys are the strings that you say to include. And the values would then be the lists of, so here's all of the documents that we embedded. And the documents were just strings, remember? The metadatas, and then all of the different embeddings. You can also look at what the embeddings are, and if you were to kind of pick one of these out, they would each be link 384. I think that was the right number. Okay, so what I wanted to do here was just show you we can compute pairwise similarity scores between each of these embeddings. And okay, conveniently, which is how it should be, if we take the similarity score between acceleration and acceleration, you get 1. So 1's on all the diagonals. That's means great. Like things are working as expected. I went ahead and the next cell will actually compute this heat map. And I think this is nice because it actually does show that kind of things work as expected. If you look at kind of the darkest values on this heat map, you can see that gravity and force are pretty well correlated in the sense that they have the pretty high similarities. Again, higher values, darker colors mean higher values, more similar. We see that velocity, acceleration, momentum, these are, I guess, like velocity is similar to acceleration and momentum, which is, as expected. And then we see another dark square here for energy, work, and power, and another dark square here for darker for friction and inertia. And so like even these physics concepts, these embeddings were just trained on text and when the text was used in the surrounding context. But it captured like similarities between these things, which is really cool. All right, so there's your embeddings in your vector database, which is just your building block for RAG architectures. All right, so now we're going to get into some kind of fun stuff. And this is, I promise, where the fun begins. And so we want to talk about extracting text from PDFs, and actually like we're going to call an archive, an API that searches archive for like research, for recently published research papers. So here you'll run a cell that loads a PyPDF loader, which will load PDFs into your notebook as text. A character text splitter, because sometimes these things are really, really long and you don't want to embed the entire document. You want to embed different chunks of it that have different meanings. Import archive, which will allow you to make that API call. And your vector database path and your directory path from the config. So, okay, great. This first cell that you'll run will actually connect you and allow you to make calls to the archive API. And so you're going to set this number to be however many results you want to get. And I gave you some options for how you actually retrieve or get your articles. You can get them by the submitted date, relevance, or last update date. And I just did an archive search for the word quantum. And I believe when I did this, I had the results set to 10. I changed it to 6 for your notebook running a bit quicker. And okay, so what did I do? I created an instance of this archive search. Okay, and then I printed what it was. So it's an archive search instance. This was my query, and this was my max results. And then I actually want to get those results and print out what they are. And so this is where we do this. So results is what's called a generator object. But to look at what those results are, we can run this cell, which looks over for R in the results. We print the title. And so, okay, we get the title of the, I think I did last submitted, or the submitted date of the last article submitted by searching that word quantum. Okay, which I think is pretty cool. And we will actually be using this archive API when we create our agentic research, physics research assistant workflow. So, okay, what else can I do? I can grab the summary of each of those articles. So that API call also has what do I want to say? I'm drawing a blank for the word, but it also has it's not okay. Well, regardless, an object that we can use to grab the summaries for each of the articles that we pulled. And then we can also access the authors for each of the articles. So your results here will most likely look different. Quantum's a pretty broad field. You know more than me about how recent these publications are coming out. And so you'll get your authors. Okay. And so what we're going to do is we're actually going to download all of those articles. So what we're doing here is we're creating a directory path. So that will create one in your system. And then if one doesn't exist already, under data dir path, where that's actually stored in the config, you could make that whatever you want. And then I think it's just called data. And then you create a data directory name, it's just quantum. And we're going to make those directories if they don't exist already. This os.path.join is a nice way of combining different path variables into a actual directory path. All right. And so, okay. This next cell, what we do is for every result in our archive results, so client.results of where you put in your search, we download the PDF and we store it and we save it in this directory with the file name that's just the title of your article. So R was the result and r.title access that title. All right. And so you can actually see or set your sample file name to title.download. And if you were to print that sample file name, you would see it's just this title of the first article. All right. And so that will take some time for you to run. Changed it to 6. That would hopefully take a little bit less time. All right. So that downloaded all of the articles into a directory called Quantum. But we actually need to grab the text. So what do we do? Okay, I'm going to load each of these PDFs using a PDF loader. And so I instantiate a PyPDF loader and I direct it to the path to where one of these PDFs are. So this is a path to one of your files, sample file path. And I use a PDF loader to actually load that PDF in as text. And what we do get is we get, when I do loader.load, I get the actual text from the entire article. There are different encoding structures that you can use here in your loader. But like we use UTF-8, I believe, is the default, and you'll get all of the text loaded from that article. Okay, it's obviously very long. We're gonna kind of skip over it. But if we see docs equals loader.load, and I look at what type it is, okay, loader.load loads a list. Okay, and what is that list of? That list is, okay, I look at the type of the first element of that list, and it is what's called a lang chain document. Okay, so what is that? That's a document stores a couple things, but it will store your page content, which is the text, and it will store any metadata for that file. That metadata is generally defaulted to be the source, so your file path, and we will see that soon. All right, so one thing that you'll notice is that it was a list. Okay, so why was it a list? Well, it loads each page separately. So so the list docs was a list. Doc 0 is the first element of that list. So that's a document. And that document, the page contents is just page 1. So page 1 is the first element of that docs list, and it's just a page. So the default when you do loader.load is to load it page-wise. All right. And then we can access the page content. So page 1 contents is, I printed that statement, and then you have all the page 1 contents. And then we can also look at what the metadata is. And so the metadata here was your source. And I believe that's all that's stored in the metadata for this. Oh, sorry, there's also the page number. So your metadata here stores the source and the page number from archive. All right, and you could specify those yourself if you wanted. Why I'm mentioning it is because when you create your vector DB, that source will get saved. All right. So I'm going to go through this part a little bit quickly, but I just want to breeze over it. So when you loaded those documents, they were loaded page-wise, but you can also choose to chunk them differently. And so you can split those documents. And we use splitting. Why? Okay, when we want to embed documents, embedding one entire paper from archive, you could imagine, like first we're probably going to hit the amount of token limits that an embedding model is allowing. But 2, it captures far too many things. Like you would lose a lot of the meaning of most of the paper because it probably doesn't have one uniform thing that's trying to say. Like different parts of the paper are saying different things. And this is true for most documents that you want to embed. So we talk about these, like maybe Mike talked about embedding spec sheets, and different spec sheets have different sections. Like this one section might be a product summary, one section might be the product features, one section might be a compatibility section. And so you embed different sections separately to capture the meaning of those sections. If you embed the whole thing, it's like averaging across the entire thing and you're going to lose out on a lot of information. So we split documents and we use text splitters to do that. One of the most common and easiest is a character text splitter. So that's just going to say, okay, I want to use a chunk size of 1,500, which is the number of tokens. I want them to overlap by 250. So if I embed this chunk, my next chunk starts before the other chunk ends. Oh, sorry, this is going to say that the chunk size actually refers to length, not tokens. And I'm going to split whenever I see a new line character. So that's going to indicate a new chunk. There are a lot of other chunking methods, and some of them get a little more sophisticated. Some of them use semantic chunking even, where you use a model to actually determine when you should do the splitting. Like, did the semantic meaning change significantly between this section and that section? Let's chunk them separately. So there's different ways to chunk your documents before storing them in your vector database or vectorizing and storing. So here you can see I split the documents. And now that single document is now really small or much smaller than it previously was, where it had to actually, like, this was it before, right? Like super long, but I actually split it now. Okay. So, but one thing to notice is that the metadata was still saved. So that same metadata was carried over. Okay. All right. So here's where you're actually going to load in your model, which this is where I would suggest saving this for later and just kind of following along. Oh no. Oh, okay, that's okay. Because it does take a little while for this to happen. You'll have to open up a terminal inside of Google Colab and load in a model. And that's where we'll load in that local llama model using something called Ollama. If you download Ollama on your local computer, so Google Ollama download, you can download Ollama, and then in your terminal, you can just run Ollama run and a model name, and you can use, I think you can use Mistral models, you can use really big llama models, you can use a Quen model that is like specific for doing doing coding. You can use a lot of different open source models and have them right there in your terminal, which I think is really nice. Depending on what I'm working on at the time, I always have one kind of on my local computer that I can pull up and ask questions or interact with or have it do coding for me. So if I'm currently like doing a lot of coding, I'll have the Quen coding model up. All right, that was a nice aside. All right, so when we now we're going to kind of tie it all together. So we chunked one of our articles that we downloaded from archive, and now we're going to we're going to chunk all of them. So we have them all saved in that directory. And we're going to set up RAG. So what I'm doing is I'm getting a model. This get LLM function was something that I had defined in a common functions file. It's a Python file outside of this environment, and it's located in your Google Drive if you want to look at it. I did that because I was also using both an OpenAI and a Llama model. And so this allowed me just to kind of swap out some of the variations and just keep that same functionality, as opposed to like remembering how to instantiate one of these models. So we specify to look at the quantum directory, and we're going to load everything in from the quantum directory. So you'll notice now we're using a PyPDF directory loader. So I pointed at it as just one single directory, and it'll load every PDF in that directory. There are things that will load different types of files. So some will load Excel files from that directory, etc. So lots of things to be done there. You can load Excel files in different formats. You can load documents. You can load all different file types. Here we're just doing PDFs. All right, so load and split. I say, okay, we're going to load everything in that directory. And we're going to split using our character text splitter. And here's what we get out. We get these nice splitted documents. So this is just one of them. This is the first. Again, we still have our metadata saved, our source and our page number. All right, so now let's put them all in a vector DB. We're going to vectorize and throw all of these archive articles splitted. So we're going to throw their chunks into our vector DB. I'll be honest with you, I did not work with the different chunking methods. I didn't optimize it for making sure like each chunk was a paragraph or each chunk was a different section of the article. None of that. So there's a lot of work to be done to actually make this like something that you could interact with a little bit better. But same thing, we create a Chroma vector DB, but this time we're going to save one we're going to create one with the name Chroma. I add all my documents to the vector DB. It's stored in it's probably stored in your Google Drive. You could open the folder here and see it. And I add all of the documents. Notice there's a lot more. So I chunked everything, and there's a lot of chunks. All right. Let's see. Where's my scroll? Here we go. Oh no. All right. Okay. So, now we see what the importance of RAG is. So, all right, if I was to ask our language model, so the Llama model 3.1 that we download, or that I downloaded, and you'll download if you run that terminal command, and I ask the question, what is the most recent article published in quantum uncertainty in the area of the black hole? Okay, so you'll see the large language model kind of gave you a very generic answer, I should say, but it's not super generic. I would love for someone to actually look and see. It may have hallucinated. There's a high likelihood these are not actual articles. But even if they were, they're from 2020 or 2019. I don't know, I'm not that like familiar with the field, but I'm almost positive because I actually found an archive article recently about this, that these are not the most recent publications. And so, my point being is that the model didn't have access to any of the data. It didn't have access to the data from the past 4 years. And so it was unable to actually answer that question reliably. And so here's where we actually create our RAG architecture. So we've got our vector DB, and that vector DB, well, okay, it's just loading in the one that you created for quantum. And doing so, I can now search, similarity search with relevance score. I put my score threshold to be low just in case. Put in my question, which was defined earlier, most recent article regarding quantum uncertainty in the area of the black hole. And then I put K to be 3, which is how many chunks I want to retrieve. And okay, so what comes back? If you look, I get the metadata. So I pulled page 0, page 2, and page 1 from, all right, it looks like, oh, wow, this article was titled Quantum Uncertainty in the Area of the Black Hole, in the area of a black hole. And the page content is listed here. So these are the three most relevant or closest to our articles or chunks from one single article actually relating to our content or our question. So now from the most relevant, that first one, I'm going to actually print the page content itself. And you'll see that there. Okay. And so, okay, great. But can we kind of streamline this a little bit? So I'm going to define the minimum number of chunks of context to use. Or sorry, and I don't want to streamline it. I want to actually like generate. So we did the retrieval. Now we want to do the generation. And so I defined this thing called a prompt. And this is what's actually going to be fed to the large language model. And what we need to do, if you remember the RAG architecture, is we need to augment. So this is the step where we actually combine the context with the user's question. And so you'll see here, we have information, and this is in brackets because how Python works, this is a formatted string. So anything that is defined as most relevant content, which I believe I defined up here to be this first page, right? Most relevant content is the page content. I printed it. It will be placed where inside these brackets. So that's how Python works with formatted strings. And then my question, which I've already defined as question, will be plugged in there. So this is actually one big string, no variables. All those variables get plugged into the formatted string. And then when I say LLM.invoke prompt, that single string, all of that, which now has the content, so your retrieved information, and your question gets fed to the language model to do a generation. And unfortunately, I must have like recently run this, or the output must have somehow cleared. But what will happen is that prompt, everything gets fed to the model, and it will actually generate an answer. So that is your retrieval, augmentation, and generation. Okay, so great. That's like, but all we did was feed one article or one chunk in for that context. So can we soup it up a bit? And we can. There's different ways, but one thing we can do is we can stuff all the context from retrieval all together. That's called the stuffed documents chain. There's other methods where maybe that would be too much context, it'd be too long for the model. So you can refine it. And there's different ways to do that. I kind of talk about them here, but one is you can use each of them separately. So you could feed the first one in, get an answer, and then you could say your previous answer was this, but here's new context. Do you adjust your answer? And it would continue through a loop. Another thing you could do is you can take all of your context, first summarize it, then feed it as context to the model as your augmented information and feed that in. And so those are your different methods. So, okay, but it gets even better. So this is what it would look like to do it kind of all in one, where you're actually, here's your stuff documents chain. We're stuffing it all in. And this is what comes out. So this is the same thing actually as the previous output that I accidentally cleared. And you get the most recent article regarding quantum uncertainty in the area of the black hole is titled Quantum Uncertainty in the Area of the Black Hole, which was prepared for submission by blah, 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 blah. Gives you the date and everything. So we did retrieval augmented generation. We got an actual relevant answer. Pretty cool. Okay. Now it gets even better. If you use LangChain, which I will caution you, is consistently updating. Like they are getting better and better and better. They're getting more functionalities, but that does mean that some functionalities are being outdated somewhat quickly. You need to make sure the package you use is consistent. If you do create like an app or something like that, but it does give us this nice wrapper. So I can create what's called a LangChain prompt template, which has things in, this is not a formatted string anymore, but it does have things in brackets. And I do input variables. This is where I define or tell LangChain what the brackets are. So it says, okay, content I want to replace and question I want to replace. And then, so this is all I need to use LangChain. One prompt template, which is my same prompt I used before, where the content is here and the question is here. You'll notice the delimiters, that's kind of and instructions are also between delimiters. It's a common prompting technique. And now all I do is I say prompt is prompt template.invoke, where I feed in what the content is. So the content is, okay, here's my retrieved content, and here's my question. And now you can see, if you look through this string, you can see that the actual, whatever was here inside the brackets did get replaced by strings, and you can invoke it and get a very similar answer. Okay, and then it gets even better. So now you can put it all in one. If you notice, even here, we had to do the retrieval step on our own. I fed in all those chunks myself using like a string concatenation, but you can create a large language model chain where you determine what the language model is, and you declare the prompt template, which is what we created before. And here's where you feed your context, and here's where you feed your question. Okay, and then it gets even better. And I'll let you work through this here, but you can even bring in so the stuff documents chain says you want to do retrieval and you want to stuff all the responses together. You define your prompt template and you get your similarity score. And then it goes through this entire chain and you can see everything that happened with LangChain and the response. All right. Whew, sweet. All right, so there's your retrieval. I will pause there for questions as I move over to my other screen when we're talking about agents.
So there are no questions in the Q&A block at the moment.
I'll take that as a positive. All right, so at least in the industry and probably online, you've seen talk about agents a lot. I'm going to breeze through, like, again, not get super technical, but I do want to introduce something called a React framework. And so what a React framework is it's combining two different methods of using a large language model. The first being reasoning, where you actually just tell the large language model how you want it to think. So let's say I want it to make a decision based on a question that's being asked, but I want it to follow a certain chain of thought. So I want it to first think about how it would solve it. Second, I want it to like describe the scenario that was presented. And then third, I want to actually, think about the actions, like think about what I should do in that scenario. And then finally act and decide and like create a response based on that scenario. So you tell it how to think. And that has been shown to really improve your responses from your large language model, giving examples or giving like a chain of thought, like how you want it to go, how you want it to think. And then there's also acting. And that's where you tell the large language model, okay, like I want you to use this different tool to accomplish a task outside of the language model. Like I want you to call this different tool and actually accomplish a task, like do addition. I want you to do math, and then I want you to bring your results back to me. That's acting. So that's when something actually is happening outside the language model itself. We can combine these two things in something called a React framework. So I'm going to first talk about chain of thought. And here's an example of chain of thought prompting. So standard prompting would be Roger has 5 tennis balls. He buys 2 more cans of tennis balls. How each can has 3 tennis balls. How many tennis balls do you have now? And the answer is just 11. Like the model answer is 11. Or sorry, I apologize. I'm wildly off. So then you tell it, okay, what you should do is answer 11. And then the actual question asked is the cafeteria has 23 apples. If they used 20 to make lunch and bought 6 more, how many apples do they have? And now the model just says, okay, the answer is 27. It hallucinated because it kind of followed the pattern of the example you gave it, which was just the answer is 11. So it was like, okay, the answer is 27. That sounds good to me. Okay, but that's really pretty flawed because, well, it's wrong. So how can you have the model do a better job? Well, you can give it an example of how you wanted it to think. And you can see here, it went, what the prompt was, so the model input is this entire thing. And you say, okay, here's a sample question. Here's a sample answer. And when in your answer, you're going to say, okay, Robert started with 5 balls, 2 cans of tennis, and 2 cans of 3 tennis balls each is 6 tennis balls. 5 plus 6 is 11. The answer is 11. So you told it exactly how to think, and then you gave it a new question, and now it went through that exact same reasoning process. And if you think about how the generation for models works, you can kind of believe that this might be true. That it would actually like adjust those probabilities for the next token and kind of adjust to your previous or instructed way of thinking. So again, the takeaway is chain of thought improves performance. Okay, so now if we talk about agents, what we want is we got to kind of combine chain of thought with agents. And so what agents are okay, we we have our large language model, and it's going to say to take actions, and then you're going to get observations from your environment that you like where you took the actions. Like let's say you did the math in this environment and you brought back the answer, and that's an observation that's brought back to the agent or brought back to your language model. So this is kind of like an agentic workflow. Due to time, I'm kind of gotta skip through, but these are at least nice to look at on your own time. And so here's an example of what React prompting looks like. So you can see here, so it's Hotspot QA, which is a sample data set to use to like evaluate large language model responses. But the question is, how many rooms are in a hotel that is home to the Cirque du Soleil show Mystere? And because the model was outdated, it just hallucinates. So the standard response is some hallucination. The chain of thought response here is here. The just action response here, where like the tool has acts outside the environment and brings the response back, is here. Okay, But here's your chain of thought, or your React agent. So it's chain of thought combined with this action. And you can see here. So you say, okay, the thought is, this is what the model does. I need to search the Cirque du Soleil Show Mystere to find the hotel it is in, then find the number of rooms in the hotel. So the first action you're going to do, and it says, okay, first go to an environment where I search Cirque du Soleil Show Mystere. So I search for it and I bring the response back. Okay, it couldn't find it. Okay, and so it goes through this like chain of thought. What is the action I should take? What do I observe from the environment? Now, what's the next thought I have? What's the next action I should take? What do I observe from that action? And it continues until it can answer a question. Cool. So, another example, but I'll let you read through that one. And so here's just some nice like readouts of what this actually, how React performs. And so action only, these are your percentages that it was correct. So on the hotspot QA data set, action only was right 25.7% of the time, reason only was correct 29.4% of the time, and action React was, which is just this method of prompting and using agents, was correct 35.1% of the time. On a different data set, here are the results. And the model used was Palm 540 billion. Okay, so nice outcomes of React. Again, kind of going to the benefits of this React system that I will let you look at because I do want to get to the notebooks. But basically, it allows your large language model to think on its own, use other environments like API calls, use math, use like other tools to do the math itself, bring it back to the model, observe the responses, and then come up with new thoughts until it gets to the answer. And so it's like this autonomous use of agents and thinking, which I think is really cool. And so here's some really practical examples of React agent use cases. Again, you'll have these slides later, so I will go ahead and leave them to you. But like, for example, social media management. So crafting social media postings by retrieving and creating material based on current trends and subjects. So this is something that would like interact with social media currently, find out what's currently trending, bring it back to the model, and then kind of recursively do this until you get something yourself that is considered trending and then post it. And so this would be an autonomous agent workflow or agentic workflow that would do it all itself. And so limitations of large language models themselves, okay, well, they can only do like textual tasks for the most part. Like, so they have their one specific task, which is just reliant on those probabilities for a next token. You can imagine that's quite limiting. But using agents, we can now use external environments, and using this chain of thought reasoning helps to mimic your actual thought process if you were to create a tool. All right, so we will now go back to our notebooks, and we're going to go to notebook 2, which is the React Framework notebook. All right, so there is a couple questions. Would you say that prompt engineering is essentially training large language models to do critical thinking in a human-like way? I shy away from using the word training only because like when we train models, it's very different. But I do like thinking of prompt engineering or this React framework as like creating one language agent that kind of controls an entire workflow. So you can have this one single language agent that has all the prompt engineering for the thought processes, And using that one language agent, you can kind of use it to direct these other agents. So like, let's say you wanted to mimic a project team. You could have one agent that is controlling what everyone does and what tasks get sent to different people. You could have one language agent that's like your project manager, one language agent that's your code writer, and something like that. And this language agent kind of directs. And so that's part of how I think of this entire workflow. Hopefully that answers your question. Okay, so we now have 20 minutes. I think it's perfect to get through part 2. I will say part 3 is really cool. It will create an agent where the agent itself, you type in a question, it searches archive based on your question. It comes up with a query is needed to search archive. And then it will come back and summarize or grab the authors or something like that from the articles. The model is, or the agent, the framework is pretty brittle. Meaning that like we had to really carefully craft it partially because the llama model is so small. But if you were willing to pay a small cost for GPT and a GPT endpoint, which is actually pretty minimal to set up on your own or to pay for on your own, it would cost you like $1 a month. With agentic workflows, it will cost you a little bit more, but it is relatively little in the grand scheme of things. You could replace that model with an OpenAI model and get really great performance, and you could like do really cool agentic tasks. So with that framework, the framework you're about to see, the possibilities are endless, and you can kind of just swap things in and out. And hopefully I wrote the notebook in a way where you can do a lot of that on your own. And again, like this is something you're interested in and like some part of the notebook is breaking for you or something, I will do my best to use the bandwidth I have to help there. Okay, so so the first thing we're going to do, very, very small task. It's nothing like mind-blowing by any means, but it does demonstrate this agentic workflow. So don't prepare to like have your jaw drop on this, but I think you'll be able to see how this can be applied and to do some like much cooler things, especially if you hook it up to an API, if you replace a lot of the tools that we're about to do with something cooler. So what we're going to do is we're going to build a physics research assistant who will help us quickly calculate basic circuit values based on Ohm's law. So one thing that we also do in here is you can go to Tvili, and this is one API that you can use, which is really friendly with large language models, and the limit for the API is like 1,000, so it's relatively large, and it allows you to like basically perform Google, Bing, DuckDuckGo searches, but like a little bit less restricted. You have an API for it. DuckDuckGo API is now very limited. You like get to I think you get 100 a month or something, and then you have to pay. So this is a very nice. It was created for large language models. It's pretty friendly. So if you are interested in building a tool that has an API, nice place to start. But you do have to log on, create an account, get an API key. Takes probably 6 minutes. All right. So all of that being said, again, we define our large language model and we can talk with it. We're going to define a chat instance. It's just kind of like a different way of using this large language model through LangChain with a different wrapper. This tool environment this thing we're about to create requires this chat instance instead. And those messages that get fed in and out of the chat model look something like this. It says, okay, the system says you're a helpful translator. Translate the user sentence to French. And then the human now inputs, I love programming. And then, okay, so that's what gets fed to the model. And then when you hit chat, when you say chat large language, when you take your chat model and you say dot invoke and you plug in those messages, you're feeding that exact prompt to the model, and it comes back as the translation of I love programming in French is, I'm not going to say that because I not good with French. I should have chose Spanish or something. Okay, so you'll see you can get the content by saying .content. This is particular to this chat model. All right. I say that because it's really helpful to see that this is the format that is expected of the chat model. It expects system or something, maybe assistant, what it said, and then something else like a user or a human and what they said. Okay, so here's where we're actually going to define our agent. So if you aren't unfamiliar with classes in Python, it's okay. All of this, hopefully, is something that you can just copy and paste and plug and play. So I'll explain the necessary portions. So, let's see. So large language model is where you plug in your large language model. The messages, that is going to be some sequence of messages that have been passed in and out of the model. It's initialized as empty, but it will have something to start as a system message. Tools, those are going to be the tools that you have available to the model. So it's a dictionary of tool names and functions. So this, well, we'll see an example of it soon. And then every time the system is run, you append messages to it, and you'll see that happen as well. So, okay, this call is what's called like when you just put a parenthesis after this, after a like after you instantiate one of these agents, if you to like want to use it, this is what's called. And so what happens when you hit call and you follow it up with some string is it will append to your messages what you said. So it will append a user said whatever the message was. So it appends this rule, user, that's you, and content message. Okay. And then so, and then what else happens? Okay, if it is a tool request, and so like let's look down to what tool request does. That says if one of the tool names is in the message, then call a tool. And if not, so if one of the tool names is in your message, handle tool request. If not, do the execute step. And the execute step is called a large language model. So this is the setup for your agentic workflow. Okay, so we're not necessarily going to worry too much about this. This is just how you deal with, this is just a little bit of parsing. Okay, so here is the prompt. And this is what is specific, and you need to change this for your different tool usage if you want to create a different tool. So the prompt, you run in a loop of thought, action, pause, observation. Just like we talked about with the React framework. At the end of the loop, you will output an answer. Use thought to describe your thoughts about the question you've been asked. Use action to run one of the actions available to you, then return pause. Basically, that says large language model, if you're requesting an action, you're done after that. Just return pause and you're done. And the large language model just stops. Do not guess or use what you do not, or use what you know. So this is saying like, don't use the model itself, like use the tools, use actions whenever you can. Observations will be a result of running these actions. And then we talk up, so that's all fine. You can keep that itself. And then we get to your available actions. These are your defined tools. So we're telling the model, you can do a voltage calculation. That's one of your tool names. For a voltage calculation, your inputs will be current and resistance. And this is what the tool does. It calculates and returns the voltage using this formula. Your current calculation is this. It inputs voltage and resistance, and this is what it does. Same with resistance calculation. Round any calculations to the nearest hundredth or you'll be penalized. This is kind of like a prompt engineering technique. The or you'll be penalized part is. And then, okay, now it gives an example session. This is important. Again, it's kind of that like zero-shot learning or a bit of a prompt engineering technique. So this says what to do. This gives an example of what to do. So you'll notice in the example, it says, this is the question that you're fed. This is the thought you should have. And this is the action. So this would be your response. And then you would return pause Okay, great. Like then the loop would, then it would be over. And then it tells the main model you'll be called again with this because you'll send it out to a tool. The tool will do the voltage calculation with these inputs. And then you'll receive back an observation. That observation will be, this is the voltage. So then you will then be able to do an answer. So you'll output the voltage is 10 volts. It goes through another example. And then like that's our prompt. Okay. So now we need to actually define the tools because if you notice here, when we define our agent, it needs to know what the tools are and what their names are. So down here, we define our tools. Tool was voltage calculation, and it has the correct inputs, and it says what to do. This is actually a Python function. We're sending it out to a Python function, the agent is, or the large language model is sending it out to a Python function and it will get the observation. And then we have our collection of tools. This is the name of the tool, and this is the function itself. We define all of those. And now, okay, this agentic bot was what we defined up here. Okay, we create an instance of one of those with the prompt, the chat model, and the tool dictionary. Okay, so when I initialize that agentic bot, what is the messages? So if you remember, like the messages was empty, and then when it gets initialized with this system prompt. And so, which is what we just did here, that prompt was our prompt, remember? And so the prompt is exactly what's printed here, because I just printed it. So I printed the messages. And right now, all the messages are, which are a list, is it's just the prompt, because we haven't done anything else. It's just the prompt. So now I want to call the agentic bot. I say, what is the voltage if resistance is 5 ohms and current is 2 amps? And this is the response from the large language model. I should calculate the voltage using the formula V equals I times R. And then it says, that means I want to do the action that is available to me, which has name voltage calculation with inputs current 2 and resistance 5. And then it outputs pause. We're done. Okay. So right now, the agent isn't very autonomous. You have to do that voltage calculation yourself. It told you to do it, so you're going to do it. And you get back 10 volts. So now, okay, what are your messages that are stored in your agentic bot now? Okay, now it's your original prompt together with the user's message, together with, okay, the assistant's message, which was the thought, together with the suggested action, together with pause. Okay, so now, okay, let's do it again. So I'm going to reinitialize an agentic bot just to watch it happen one more time. Okay, so now I initialize it, which means the system prompt is reset, or the messages are reset to just be the system prompt. I feed in my new query, and now I get a new response. I should calculate the current using the formula I equals V divided by R. That's a current calculation. That's my action with inputs voltage 27 and resistance 9. Okay, so then now I go on my own, which is inside this environment, and I do the current calculation. And then, okay, that needs to go back to the model. So I form it as an observation. So this is the string. Observation, current 3 amps. And I am going to, so those were my messages. You'll notice it stopped at action and pause. So then I need to add observation to the list of messages. So I do so. And so I add this next prompt, which was observation. This next prompt was observation, current is 3 amps. I feed that to the model. And now the answer from the model is an answer, and it's done. So that was your agentic workflow. And now you can walk through all of the messages. So the message was, the system had the original system prompt. The users asked this. The assistant had its thought and its suggested action, and then it paused. And then you have a new observation, which was given back by the environment, which was just the user right now, or that Python function together with the user. And now you get an answer. Okay. So that was like kind of cool, but it wasn't really that cool because like I still had to be involved. I could have I still had to like do the calculation or tell Python to do it. But can we automate it? And we can. So essentially, I'm going to skip over this part and just go to the automation. And well, okay, yeah, let's just go to the automation. And so what we do is we define, let's see what time is it? It'll be 6 minutes. So I'm going to breeze through this, but it basically says, I'm just going to walk through the pseudocode. So you initialize this agent with the system prompt. Then you input a question, which is assigned to the user rule, and the content is your question. And the assistant has a thought and a suggested action. If an action is in your tool dictionary, it's in that name, it's going to actually go to the environment, do the action, and bring back the observation until the action, until like the thought is no longer an action, or whatever you defined as the max number of iterations possible is reached. And so we're going to use the tool dictionary that was defined earlier. And so, sorry, with it being so big on my screen, it's hard to actually like see the entire context, but you define your known actions. And then we say what to do if you have an action input. And this says, like, if you have an action input, actually like get the name of the action and get it, and then so that you can call the tool. So if actions, do the action, and if answer is in it, then return just the answer and stop. So let's watch the whole thing happen. If this is your voltage and resistance is this ohms, what is the current? And you set the max turns to 5. So that's all I do. I query with the question and the max turns, and query was defined by here. So let's see what happened. Okay, on turn 1, the next prompt was my user's response. The bot responded with the thought I should calculate the current using this formula. The current calculation is this. The bot paused because we split the lines, determined what the action was, which was current. Oh no. Oh no, what did I just do? I don't know where it all went. Okay. Oh, it went up. Sorry, I just lost myself. Cool. There we go. Which was current calculation, and then it ran the current calculation, and then the agent executed and got an observation of this. Observation, not final answers. This is the current. Turn 2 had this observation. The bot's response was an answer. Since answer was in the response, it stopped and it gave the answer. Okay, so that was the whole thing. It ran automatically. So here again, LangChain has a really nice wrapper for this React agent workflow. We can modify what that is because we want to make sure it uses tools, so modify their prompt slightly here. But again, we can we need to have different tools. So we define tools a little bit differently when we feed them to LangChain. But when we define our tools, as long as you have this really nice string here, which defines the inputs and what is, what the function is doing, that's all it needs. And so you use this decorator, this tool decorator, and you can actually see what this tool is. And then we also want it to be able to do math. So I load this this math tool, and then I add my tools that I was just defined. And so here's my list of tools. Now I can use this LangChain's create React agent with with my large language model, with my tools, and with my prompt. And I create an agent executor, and then here's my actual agent. When I feed it this exact question or input, so input, what is the resistance? You can see exactly what the agent did. Action, it says thought. To find the resistance, we need to use Ohm's law, which states this. The action is resistance calculation. Here are the inputs, the action. Here's what the output of the tool was. That's why it's a different color. Here's the step. And so you can walk through the exact thing, and then you end up with your answer. Okay, cool. So that's your React agent workflow, going through somewhat quickly, but hopefully it's something where you can swap these tools in and out. And with a better model, if you define these tools, which I'm going to give you a different example of these tools here, in this, where's my tools? Oh boy. Yeah, here you go. Here's a tool decorator. So this is a little more accurate in this part 3 notebook of how to actually define tools with really nice doc strings that define what the function is. These are really helpful for the for the large language model agent to know how to use the tools. The more descriptive these are, the better. But doing so, you can replace any of the tools and create your own agentic workflow with different tools. In here, one of the tools is searching archive. And so you can you can define a language agent that is able to go and do an archive search, bring back the results, and do other things like summarize and things like that, which I think is pretty cool and fun. So, that's all I have for you today. I want to say thank you for the opportunity to speak and talk with you. Again, I moved from being a pure math algebraic number theory PhD into AI and machine learning. So please, I encourage you, like, if you're thinking about it, but it's a little bit daunting, it's very reasonable. Yes, there are plenty of people with experience in the field, but again, it's one of these fields where it's really helpful to have various backgrounds to work across industries. There are plenty of physics applications that we encounter day to day that you all would be great and have expertise in.
Alexis, thank you so much. It was incredibly impressive the way you've chained so many of the operations together. I hope people will, I'm sure people will have to in their own time try to follow through that. But I know you and we should mention Chongwen Liu, graduate student from here at Brown, who worked with Alexis to get it into the Google Colab virtual machine language. You can reverse engineer back to the original form, which was to run on your own local machine. I think Alexis code does that. But either way, we know that it does work as per the instructions that are in the notebook for the Google Colab. You do have to, this pro, I'm afraid, again, we ran into the computation and accessibility option issue. Means you have got to spend a few dollars, $10, I think it is, on pro. But anyway, so that's the end of the entire winter school. I hope all 7 modules have covered the sort of some of the parameter space in the AI. We, as you can see, both from Alexis's presentation, but also from the previous presentations, we're trying to be as practical as possible, really show you fully worked examples. I will say the comparison between, for instance, what we were able to do at this winter school and the level of the technology even just a year ago. I mean, I think you mentioned, or in the slides, that you were saying that Stanford researchers had put a number on the rate of the two-folding time, and they're claiming that it's 3 months for AI, not 18 months, as it is in Moore's law. So for this factor of two, gain in power, which of course, I think that is genuinely noticeable if you look at what we were able to sort of showcase at the last winter school. What we are at this one, heaven knows what we'll be showcasing a year from now. But anyway, thank you again. Really appreciate the presentation. Thank you to all of those who have participated, those who are with us now. We will, as far as the submissions, there were opportunities in a number of the worked notebooks for you to sort of aggregate, to commit material to the across by using the specific workbook and actually uploading something through the Google form, which is linked in the on the shared drive. Do please, if you are planning to run the notebooks, do please go ahead and consider doing that. The instructors or the presenters from each module are looking at the submissions. You will see them posting in the shared drive that information, based on the aggregates, and also mentioning a number of the people who did the more interesting submissions. So yes, as far as the drive is concerned, it will remain available to all those that have applied through Indico for access and have been granted access. You will continue to be able to get access, so don't worry about any of that material going away. You don't have to download it all in one go. We'll make sure we keep the access there. The Indico site as well that you've registered through, we run that as well, and it will remain in place. Otherwise, I just want to thank Ariel Green, as I did at the beginning. We've now made it through the week and all the way to the end, and she's done an absolutely fantastic job organizing it, as has Sean Dubier, who also has been involved, and then there are a whole series of other people you've heard thanked during this session. And thank you again, Alexis and Michael, Luck, for presentations today. So thank you, all of you. I think the oh, sorry, recordings. Yes, sorry, somebody's asked a question about recordings. The recordings will be going up pretty shortly. It may be, I hope it's going to actually happen on Friday. If it doesn't happen early Friday, it'll be late Friday, but we'll get all those recordings. So you use the Indico. No, sorry, actually, it's easier for me to say it. The Brown Physics YouTube channel, it will be linked from Indico, the timetable we have, but it put bluntly, it's Brown Physics' YouTube channel that you will see those. So if you haven't subscribed to Brown Physics YouTube, please do go ahead and do so. We'll be posting any information like that will get posted to the Indico front page, so you can see any follow-ups that you want. And otherwise, we look forward to hearing from you if you have feedback. Oh yes, sorry, that's right. Ariel did ask me to mention that we will be emailing everybody on the participation list. Will get a feedback form. It really helps when you're organizing these kind of meetings to get your impressions. So please, if you can provide any feedback through that mechanism, it'll be enormously appreciated. We're trying to keep the spam emails to a minimum, although apparently we failed on Monday because somebody started spamming the mailing list. We shut that down now, but you will get a bit of mailing from us, but we'll keep it to a minimum. Okay, anyway, thank you all very much. Those of you who I've interacted with, enormously enjoyed it. And please, keep up the interaction. We are definitely in exciting times. Okay, thank you, everybody. So with that, we call this 2025 Winter School here at Brown for the AI to an end. Thank you, all of you who participated. We really appreciate it.